Hello students. Hello students. Welcome to the physics session. Today we will discuss mechanical properties of solids. Try to join the session at 1:30 p.m. Okay? Waiting for you guys to join at 1:30 p.m. Okay. Welcome everyone. Right, let us start the next chapter, mechanical properties of solids. So, keep watching this. If any message comes in the chat box. Right. Masters, am I getting my voice clearly? Yes. Very good, super. So, write down the heading, mechanical properties of solids. Mechanical properties of solids. Mechanical properties of solids. Right. So in this, first I will give you an outline of what are the concepts we are going to discuss. Then we will cross check one by one. Okay. First we will see briefly what is some terminology. Into the terminology we are not going into the deep. Okay. You have to have some idea about this terminology. Let us go ahead really quickly. So the basic terminology like what is already in system of particles and rotational motion, you already have an idea of what is a rigid body. So you can write it as some terminology under this terminology. Under this we will discuss briefly about rigid body and what is deforming force or external force and internal force or restoring force. Restoring force. So rigid body, and then we will discuss briefly about deforming force, and then restoring force, Then we will discuss about the actual concepts of this chapter. One of those is stress. What is stress and types of stress, and some basic points about this, and then strain and types of strain and some basic points about this. Okay, and after that, we will discuss briefly what is elastic limit. What is elastic limit, and then Hooke's law. And by making use of this, we will discuss one very important concept called modulus of elasticity. Modulus of elasticity. After this, modulus of elasticity and types. Actually, after stress and strain itself, here it's after itself. Before this, we need to discuss one other important concept called stress strain curve. Okay, so better we'll see. Before this, we'll see stress strain curve, then modulus of elasticity. Even before Hooke's law only. We'll see briefly about stress strain curve. To understand, we need to have an idea about this also. Okay. Hooke's law. Then only we'll deal with a stress strain curve. Stress strain curve. Then we will discuss about moduli of elasticity or modulus of elasticity and types. Especially we can classify these stress and strain into three types. Based on these types of strain or stress involved, we can classify this also into 3 types. So 3 types. We will discuss about those. Then we will see few related points like what is Poisson's ratio or Poisson's ratio. Okay. Poisson's ratio and some again related terms like how to find what is thermal stress and how to find the elongation of any body due to its own weight. Here, as part of in terms of Einstein modulus only, elongation of a body due to its own weight, and then combination of wires or rods. These points we will discuss, and then we will wind up the chapter. Okay, some examples we will deal with based on this every term. So let us start with first the basic terminology. So write down the heading. Basic terminology. So what is under this? We'll see first what is rigid body. What is rigid body? Already in system of particles we have discussed about actually rigid body, system of particles. System of particles of a body or rigid body. So rigid body is nothing but any object or a body which it is made of or comprised of number of particles, atoms or molecules. So that if you apply external force on it, the position of the particles will not change, or the shape of the body should not change. That kind of body is called as rigid body. Means every particle in the body are tightly bound with one another. So on applying external force, they will not be disturbed or they will not be deviated from their positions. Such body is called rigid body. Okay? So a body which does not change its dimensions on applying what? External force is called rigid body. Whereas here we come across the next term called what is deforming force. Deforming force. Deforming force. Deforming force is nothing but external force. The external force which produces change in dimensions in your body is called deforming force. The external force which produces change in dimensions in your body is called deforming force. That means which deforms means changes the dimensions, shape and size. You have a rod from length, you apply an external force, it changes the length, it means the dimensions, its size or shape. If you have a sphere, you apply some deforming force in all directions, external force. So the body, if you have a plastic body, it will squeeze. That means it will, the external force will changes the dimensions. It may decrease the volume. Right? This kind of forces are called deforming force. Whereas the restoring force. Actually restoring force is nothing but internal force. The force which develops inside the material, which tries to regains the original dimensions of the body is called restoring. Which tries to restore original configurations of the body. So write down the internal force developed in a body. The internal force developed in a body. The internal force developed in a body. The internal force developed in a body, which regains the original configurations of the body. Which regains or tries to regain. Okay, either we can write. Which regains the original configurations of the body, or which restores the original configurations of the body is called restoring force. Restoring force or restoring force. The internal force developed in your body which regains or restores the original configurations of your body is called restoring force. These are some basic terminology in it. Now, let's get into the actual concept called what is stress in a body solid. Especially we are discussing about mechanical properties of solids. Some of the mechanical properties are stress, strain, the modulus of elasticity, etc. So now let us discuss what is stress. What is stress? So write down the heading, subheading, stress. stress. So, briefly, if you have rigid support, to this you have attached a wire or rod of some length L and area of cross section A. This is having some area of cross section A. And now, you apply a force on this normally, external force. We also call it as deforming force. The moment you apply a force, so for example, to understand this, let us consider a rubber band. We take rubber band, if you hold with one hand, and with the other hand, if you stretch it, what happens? The moment you apply the force, it is stretched by small amount or larger amount. And if you release the applied force or external force, what happens? It will again comes back to its original length. Right? So here the applied force is called deforming force. The moment you apply the deforming force, the force will develop in the body, tries to regain the original configurations, that is called restoring force. So because of that, when you remove this applied force or deforming force, the restoring force restores the original length of the body. In this process, when you are applying a force and you are elongating the body, right? So this force on which area you are applying, usually it will be a normal force. You are applying normal to the surface. So the normal force per unit area. How much force you apply, exactly that much amount of restoring force will develop. Exactly that much amount of restoring force will develop. So you can also say that restoring force per unit area. The restoring force per unit area is called stress. So write down stress. If there is no separate symbol for stress, the different books will give you different symbols. You can use the symbol sigma. So for example, stress sigma. Sigma is equal to what? Write down restoring force per unit area or internal force per unit area. Restoring force per unit area. It is given by sigma equal to restoring force by area. Restoring force per unit area is called stress. Restoring force per unit area is called stress. It is given by sigma equal to this. This can also be expressed as force. Restoring force per unit force, it is a force. So you can write it as F by area is A. So this is the mathematical expression for stress. Stress is given by sigma equal to F by A. Copying or not? Guys, I last was? Go down. So it is given by stress sigma equal to force by area. Right? Sigma equal to F by A. So from this, we can give the units and dimensions of this. How to measure it? How can we measure this? As it is force by area, it can be measured by using a unit called unit of force by unit of area. What is the unit of force? Newton area meter square. So write down next one. Units and dimensions of stress. Units and dimensions. Dimensions of stress. First one, SI unit of SI unit of stress is what? What? Everyone. What is this? Newton per meter square. If you observe, it is force by area. But in mechanical properties of fluids, it is completed, right? There we come across one parameter called pressure. Pressure. What is the formula for pressure? Force by area only. So unit of pressure is same, Newton per meter square only. But we have given a special name to that. This Pascal. So this also can be called as Pascal. SI unit of stress is also Newton per meter square or Pascal. Pascal is denoted by PA. Pascal denoted by PA. Pascal denoted by PA. Is it clear, everyone? Right? What is the dimensions of the dimension formula of stress? Write down quickly. Dimensions of stress. Stress sigma. Use the symbol here. Stress is, if you write in dimension equation form, is equal to Newton per meter square. Force by area. Force by dimension formula is M power 1, L power 1, T power 1 is 2 by L power 2. So L cancel, 1 L comes numerator. So it becomes what? M power 1, L power minus 1 and T power minus 2. This is the dimensional formula of stress or pressure. We get a question like this. Which of the following quantities have same units and dimensions? Stress and pressure, and stress and work, and pressure and force. None of this. I think options. So you have to have an idea about it. what is the meaning of stress and what is the pressure. Stress and pressure both means same, right? Even you will come across one more quantity called Modulus of Elasticity. That also we have possess the same units. That we will see later. This is briefly about what? Stress. Stress is a scalar quantity. It does not possess any particular unit. Okay? A particular direction. So stress is a scalar. Now let's see few more points here is types of stress. Types of stress. Quickly. Write down quickly. Types of stress. When you apply a force on a given area, force per unit area is called stress. So when you apply this force, depending on this nature of force, the change in dimensions takes place in the body. Depending on the kind of change in dimensions which are taking place, you can classify the stress into three different types. Those are nothing but, the first one is longitudinal stress. Longitudinal stress. This is further can be classified into two types. One is tensile stress and compressive stress. Compressive stress. First of all, what is longitudinal stress? I don't want to give you the every definition. We will not get enough. We are not having enough time to take all definitions. Only the concept, basic concepts, and especially mathematical relations. Just we will go ahead and we will try to work out some examples. So longitudinal stress is nothing but stress is force by area. The force by area, force per unit area, which produces change in length in the body is called longitudinal stress. Change may be increased or decreased. If the force per unit area produces increase in length, the concerned or the corresponding stress is called tensile stress. It relates with increase in length. Whereas the force per unit area produces decrease in length. That means instead of applying the force like this, if you apply the force like this, it will compress us. So the length will decreases. So the force per unit area or the stress which produces decrease in length is called compressive stress. Is it clear? That is briefly about longitudinal stress. The second one is shearing stress or shear stress. Shear stress or shearing stress. Here, in case of longitudinal stress, usually normal force will involve. Whereas in case of shear stress or shearing stress, tangential force will involve. That means if you have a cylindrical body like this, and if this is attached or fixed to some rigid body or attached to a rigid body, and if you apply a force like this, a tangential force on this area, this will just move like this, so that this will displace us. The vertical surface displaces some distance, or this distance is L, this displacement is X, then the tangential force produces change in shape without changing volume. Such kind of stress will be called as shear stress. The stress which produces change in shape without change in volume is called shear stress or shearing stress. Whereas another one, third one is on bulk stress. Bulk stress is also called as volume stress. Bulk stress or volume stress. So simply, it is also force by area only, but normal force by area which produces change in volume. Change in volume is called bulk stress. The stress which produces change in volume. The stress which produces change in volume is called bulk stress. Is it clear? Or volume stress also referred as volume stress. This is briefly about stress and few points about stress. Now, let us see what interrelated parameter. The moment you apply the force on a given area, whether normal to the area of a wire which is having some length or any spherical object, whatever it is, change in dimensions will take place. So based on this change in dimensions, you can say what kind of change in dimensions are producing. We will classify this. Depending on the type of the change in dimension is taking place, we classify this. We introduce one more parameter and erasing this. So try to remember this. One by one we will try to cross check. Stress and types are over. Now let us see strain. Okay. So what is this strain and what are these different types of strain? We will see. What is strain? Write down a subheading, strain. Write down a subheading, strain. What is this strain? In general, we define a strain as the ratio between change in dimensions to original dimensions is called strain. So write down ratio between, or you can say change in dimensions per unit, original dimensions. So in general you can say ratio between, write clearly the definition. The ratio between change in dimensions, and original dimensions is called strain. What is stress? Restoring force per unit area, force by area, right? So there, while discussing the types, the longitudinal stress or shearing stress or bulk stress, you have to remember that all the stresses can be expressed as force by area only. In case of longitudinal stress, normal force by area. Shearing stress, tangential force by area. Volume stress, normal stress by area only. Okay? Right. Strain is ratio between change in dimensions by original dimensions. That dimension may be length or volume or anything. So if you take length, the force which is producing change in length, then the ratio between change in length by original length will be called as linear strain. Change in volume by original volume is called volume or bulk strain, whereas we come across differently. And the ratio between change in displacement of the fixed surface, the surface on which the force is acting by the fixed distance between these two is called shearing strain. So shear strain is little different parameter. You have to understand this carefully and you have to remember. So we can say as it is change in dimensions by original dimensions, what we can say about its units and dimensions? What is SI unit of strain? SI unit of strain is what? Is dash. Say for example, the change in length by original length. Change in length will be in meters, original length also will be in meters. Meters cancel. What will be the unit? Change in volume by volume. Volume unit by volume unit will cancel. So no unit. So you can say strain is a unitless and dimensionless quantity. Write down that. Strain is, here you can say, is means it is unitless. So in general you can write strain is unitless and dimensionless. It will not have any dimensions also. Strain is a unitless and dimensionless quantity. Next, let us write down quickly types of strain. First one, longitudinal strain. Longitudinal strain. It is defined as change in length by original length. So directly I am giving mathematical expression for this. Delta L by L. You can write in words. Change in length by original length, that is equal to delta L by L is the formula for longitudinal strain. Next, second one, shearing strain. Shearing strain, to understand, try to draw this diagram. Like you can write this is what? Cylinder. This is fixed surface. And distance between the top surface and bottom surface is L. If you apply a force, tangential force on FT, let us say, tangential force on the top area, so this will, the vertical surface tilt through an angle theta. This angle can be called as shear strain. Angle through which vertical surface tilt through or applying or application of tangential force is called shear strain, or the ratio between the displacement of the vertical surface and distance between the displaced surface and fixed surface is called shear strain. So it is denoted by, you can say, theta is equal to x by L. It is also distance by distance. Meter by meter, cancel. It also will not have any unit. But if you can measure this in terms of angle, you can express this in terms of radian. Okay? Whereas the third one is bulk strain or volume strain. Bulk strain or volume strain. It is defined as ratio between change in volume and original volume. Ratio between change in volume and original volume is called bulk strain. So write down this. These are briefly what is a few points about strain. What is strain and what are different types of strain and how to express them mathematically. Now we come across the next point called elastic limit. What is this elastic limit? So write down some heading, elastic limit. Elastic limit. What is elastic limit? If you observe a simple case, this example only. Let me erase this and redraw this clearly once again. So not like the cylindrical object, a wire, cylindrical shape, the wire you can take. It is a wire having length L and you are applying a force here. You are following everyone. This force you can apply physically by pulling, or you can attach a tag here and you can put some loads here. So mg will act. That force equal to mg will act on this area, so that produces the stress and hence strain. Because of this, the strain will produce here delta L. Are you following everyone? So if you add one more load, a mass m, if you add, force will be mg. One more load of mass m, 2 mg. One more mass m, 3 mg. Like that, force will be increasing. What force? This is called external force or deforming force. External force or deforming force. At any point, if you remove this load, it means that deforming force, the body regains complete configurations, complete length. You are following this? But if you increase this load beyond certain limit, or if you continuously increasing this load against the force, a stage will reaches, and beyond that, if you remove this load, the body will not regain its original configurations completely. Is it clear? That maximum value of force per unit area, we call it as maximum value of the force per unit area, or maximum value of stress, is called elastic limit. It's called elastic limit. So write down the maximum value of stress. The maximum value of stress. The maximum value of stress within which the body regains its original configurations completely. The body regains its original configurations completely. Is called what? Elastic limit. Is called elastic limit. Is called elastic limit. So what is that? The maximum stress. The maximum stress within which the body regains its original configurations completely. The configurations can be length or volume or anything. Okay. Within which the body will regains its original configurations. Or you can also define this as the maximum value of stress above which or beyond that the body will not regain its original configurations completely, on removal of deforming force. That is called as elastic limit. Right? Now, based on this, we come across one more term, very important term here, is called as Hooke's law. So write down as subheading Hooke's law. Hooke's law says that. You can write the statement afterwards. First listen. Hooke's law says that. See here, in this case, if you apply some deforming force, the change in length increases. Right? And if you again increase the add the load, length increases. And if you remove it, it regains. But it means the adding load means you are increasing the force on this area. So you are increasing the stress. If you increase the stress, change in length increases. That means strain also increases. Delta L will give strain, right? So strain also increases. So it is observed that stress and strain are directly proportional to one another within elastic limits. That observation is actually made by a scientist called Hooke. So it is called as Hooke's law. Are you following everyone? Right? So write down this statement. What is Hooke's law? Within elastic limit, stress is directly proportional to strain. Stress is directly proportional to strain. Within elastic limit, stress is directly proportional to strain. This is called Hooke's law. 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 Okay? Hooke's law. So what is Hooke's law? Hooke's law says stress is directly proportional to strain within elastic limit, or within elastic limit, stress is directly proportional to strain. Either way you can take it. The sentence you can reverse the words also, no problem. The meaning should be proper. Okay? What is called as Hooke's law? Even while getting the questions, you may get direct questions also. Theory based questions. Right? Which is the statement of Hooke's law. Same things will be given. So stress is directly proportional to strain within elastic limit, beyond elastic limit, irrespective of elastic limit, none of this like that. Okay? So we have to choose the option appropriately. Next, based on this, so mathematically you can write this. Mathematically you can write this as stress within elastic. You can say stress is proportional to strain, comma within elastic limit. Within elastic limit, you can take it as real elastic limit. So stress is as it is proportional. If you replace this with some constant, you can write it as a constant called E into strain. So within elastic limit, within elastic limit. So when this proportional to constant is called as modulus of elasticity. Proportional to this constant is called as modulus of elasticity. So hence you can write E is equal to stress by strain, comma within elastic limit. So the ratio between stress and strain within elastic limit is called modulus of elasticity. This is a very important term. The ratio between stress and strain within elastic limit is called what? Modulus of elasticity. This modulus of elasticity is further classified into different three types based on the types of stress and strain. Before going to the types of those moduli of elasticity, we'll see based on the stress-strain relation only one very important concept called stress-strain curve or stress-strain graph. So you can erase this, right? So write down as heading stress-strain curve. Stress-strain curve. Stress-strain curve. Stress-strain curve. What is this stress-strain curve? It is nothing but a graph. Stress-strain curve or stress-strain graph. So you can define this as a graph drawn by taking strain on x-axis, and stress on y-axis is called a stress-strain curve. It's a graph. The graph drawn by taking strain on x-axis and stress on y-axis is called stress-strain curve. What it represents is if you have zero stress, you have to deal with, you have to understand the relation between these two with respect to stress and strain. Yes? Following? Right. Stress is what? Force per unit area. Yes guys? Following everyone? What is stress? Force per unit area. Force by area. Force by area is called stress. So what is stress? Force by area. Simply force by area. Restoring force by area, external force by area, whatever it is, this force by area. So if you apply some force on this area, you can say you are applying some stress. Because of that stress, the length may increase by delta L. If you add some load here, stress increases and hence strain also increases. If you add some more load, strain increases. So that means if you increase stress, strain also increases linearly till certain point. If this is gone, we mark this as A. And this point A is called proportional limit. A is called what? Proportional limit. Based on this graph, you will get some questions, direct questions. So try to draw this graph carefully and remember the points. Beyond this point called proportional limit, what happens is if you add some load, a small same amount of load, but strain increase will be more. So stress and strain will no longer proportional to one another. That means for small stress, strain will be more. strain will be more, strain will be here for some amount of stress, strain also will be proportional, but here a small amount of stress, strain is this much. Strain increase will be more than for small stress, but they are not proportional. Okay, and this point will be called as, will be represented as B. There, and this point B will be called as yield point or elastic limit. Elastic limit. This is proportional limit. B will be called as elastic limit or yield point or yield point or yield point. What is this yield point or elastic limit is? If you increase the stress beyond this point, permanent yielding will take place, means permanent strain will produce. If you remove beyond that point, the permanent increase in length is produced. So hereafter, if you just after reaching this stage, even without increasing the stress, the body will increase its length on its own. So that point is specifically called as here. Actually, this we can also express here to some extent. Here, after reaching some point, its length will increase by its own. So it is called as self-yield point. So C, not just C. For some objects, both will be coincides. So yield point, self-yield point. C will be called as self-yield point. Self-yield point. And it will yield on its own to some extent and it stops. And again it increases the stress, strain increases, and after reaching a point called this point represented as D. After reaching this point, even if you are not increasing stress, that means load also, strain increases. Strain will increases in the load, and finally it breaks at some point E. So the stress corresponding to this point D will be called as what? Ultimate strength of the body. It is represented as a sigma x. And the stress corresponding to this point E will be called as sigma y, is breaking stress or breaking strength of the body. Are following this? Sigma, the stress corresponding to point D in the graph is called ultimate strength. That is sigma x. Sigma x is ultimate strength. Ultimate stress or strength. Stress, ultimate stress or strength of the body. And sigma y is called breaking strength or breaking stress. You can also write it as stress only, ultimate stress. Sigma y is breaking stress. Breaking stress. Whereas this point E will be called as breaking point. Whereas point E will be called as breaking point. Are following everyone? Breaking point. Breaking point. Whereas here itself, if you observe beyond D, if you increase the load, it will the length will not regain back completely. So the permanent length will increase, that can be represented as O dash. The O dash is called permanent set. O dash is called permanent set. So these points you have to remember carefully in this graph. Based on this stress strain graph, you can classify the materials into different types. Brittle materials, ductile materials, malleable materials. Malleable materials. So you can classify the materials based on stress strain graph. So here, till point A is called proportional limit. Stress and strain are proportional to one another. But till B, they are not proportional, but still it is called elastic limit. Till here, beyond, within which, and anywhere if you remove the load, the body will regain conservations completely. So till here, the wire will satisfy Hooke's law. So this is called as elastic region of the body. Elastic region, we call this as elastic region. Elastic region of the wire. So beyond this, the region is called as plastic region. Plastic region. So means elasticity is produced beyond that. That's why it is called plastic region of the body. Is it clear, everyone? Now, so we are not going to the details of so many points we come across here, like elastic. What is elastic fatigue? Elastic after effect. Some theory related points. Morally we will see, and we will try to concentrate a little more on the concepts which are having mathematical application needs, which are having mathematical relations, and which need for working out numericals. So this is briefly about this. Okay. So next, managing this. Copied everyone? Yes, boys. So, based on stress strain curve, you can classify the materials into different types. So that also try to have a point here. Types of materials. Types of materials. So those are nothing but brittle materials. Brittle. So the materials which are having less plastic region. Means once the elastic yielding point comes, it will break. It will not have any plastic region. Those are called as brittle materials. Whereas the second one is, you can say, malleable materials or ductile materials. Ductile and malleable materials. Brittle materials, ductile materials, malleable materials. These will be smooth ones, so they will have, both will have longer plastic region, but provided ductile materials and malleable materials. Ductile materials will be having large plastic region and they will be used to make large thin wires. Thin wires. They are used for making long thin wires, but these are used for making thin sheets. Thin sheets. So these kind of materials are called as ductile, what you call malleable materials. Both will have longer plastic region. Okay. And so you may come across one more kind of material called elastomers. Elastomers. The materials which possess, actually, there is a property called elastic fatigue. So that means the materials which regain their original configuration, but after so much of time, those kind of materials are called as elastomers. Elastomers. Okay? Elastomers. And they will not follow Hooke's law. The materials which does not follow Hooke's law are called, you can also say, that way also, the other way you can say, the materials which does not follow Hooke's law are called as elastomers. Example, you can say tissue of aorta, that will come under like in our human body. Okay? Tissue of aorta. Tissue of aorta is one of the examples for elastomers. They will not follow Hooke's law. So that means if you take stress and strain, so that the graph will come like this, variation will come like this. So it will not take a straight line. If any material, for any material stress and strain, the graph is a straight curve. So that kind of materials are called as, will be classified, will be called as what you call the materials which are obeying Hooke's law. So these are the materials which does not obey Hooke's law. So one of the material is tissue of aorta. Okay, this is briefly about another few points like what classification of materials. Now here, next let us get into this. That is briefly about stress strain curve. Next let us get into the main, very important concept of this entire chapter. That is modulus of elasticity and types of moduli of elasticity. So to understand this, we have to get into the Hooke's law and we have to come back. What is Hooke's law? Stress is directly proportional to strain within elastic limit, right? From that, when I erase this, Hooke's law says stress is directly proportional to strain within elastic limit, right? From that, we got one quantity called E is equal to stress by strain. So ratio between stress and strain within elastic limit is called what? Modulus of elasticity. So depending on these types of stress and strain, they are classified into different types. Write down next, write down types of moduli, moduli of elasticity. They are classified into three different types. One is Young's modulus, it is denoted by Y. Second one is bulk modulus is denoted by D. Third one is rigidity modulus. Rigidity modulus is denoted by capital G or eta. Some books will give you the symbol eta also. Okay? That is Young's modulus, bulk modulus, and rigidity modulus. Briefly, I will give you here definitions and mathematical relations. Try to copy this quickly. Young's modulus is defined as Ratio between longitudinal stress and longitudinal strain. What is this? Ratio between longitudinal stress and longitudinal strain is called Young's modulus. So mathematically you can express it as longitudinal stress is force per unit area. Longitudinal strain is delta L by A, delta L by L, delta L by L. So mathematical formula for Young's modulus is F L by AL, A into delta L. Okay. Because bulk modulus is defined as bulk stress by bulk strain. Bulk stress or what do you call? Longitudinal stress both are force by area only, normal force by area. So they write it as F by A only. But bulk strain is nothing but change in volume by original volume. So we will write it as delta L by L. Sorry, delta V, volume change. Delta V by V. So F V by A into delta V is called what? Bulk modulus, mathematical formula. If we are applying the force and hence volume is decreasing, change in volume will be taken as negative. So sometimes this can be expressed as F by A can be expressed as P, pressure by PV, pressure into V by delta V also. If the change in volume is negative, then we will take negative sign. Negative sign will be taken for decrease in volume. Positive sign will be taken for increase in volume. Here also, negative sign will be taken for decrease in length. Positive sign will be taken for increase in length. That you have to keep in mind. Okay. Whereas rigidity modulus G or eta, we use symbol here eta. It is defined as shear stress by shear strain. Write down shear stress by shear strain. Eta or G is equal to shear stress by shear strain. Shear stress by shear strain. Shear stress by shear strain. So it is equal to shear stress tangential force by area. Shear strain can be taken as theta or tangential force by area. This theta can be taken as x by L also, depending on the diagram. You have to remember the diagram. What is the diagram? If you have cylinder, you can consider even cube also. This is fixed. Apply a force, tangential force on this area. This will displace us through small x, distance x. This is capital L. So this angle twisted is called as theta. Theta is called x by L. So theta can be expressed as x by L. So this way also express. So draw this diagram once again so that you can remember how to express that. This is briefly about rigidity modulus. Okay. So while doing the numericals, usually by giving all these parameters, you may ask to calculate Young's modulus, or Young's modulus will be given, force, area and length will be given. We will ask you to find elongation, delta L. Then you can write delta L is equal to FL by A to Y article. Got it? So this kind of numericals will come. So depending on the given data and what you are asked to find, you have to redraw this formula and you have to work out the asked parameter. Okay. Next one is, these are briefly about moduli of elasticity and their types. Next one is Poisson's ratio. We'll see briefly what is Poisson's ratio. Can I erase this? Yes, Poisson's ratio. Poisson's ratio. Poisson's or Poisson's ratio. We pronounce it as Poisson's ratio. Poisson or Poisson's ratio is denoted by sigma. Here don't confuse with this letter sigma here and we have used it for stress. Okay? If it is used for stress in the question, okay, you have to follow that as a stress. Otherwise, you have to use this sigma to represent Poisson's ratio. Usually the symbol will be used, it will be mentioned along with the term first. Then you have to follow that. Okay? Poisson's ratio is defined as the ratio between lateral strain or the longitudinal strain. Ratio between lateral strain and longitudinal strain is called Poisson's ratio. To understand this, again let us see this diagram. We have a wire of length L and it is area A. So area is nothing but for circular cross section pi r square. Pi r square. Okay? So here, if you apply a force, this is radius r, so you are having pi r square, area is pi r square. If you apply force, if you apply a force, length may increase. When length increases more and more, the area, the wire becomes thinner and thinner. That means area will decreases. Radius and hence area will decreases. Yes or no? The wire becomes thinner. So if you apply a force, so that means the dimensions, not only length is decreasing here, radius also will decrease. In perpendicular direction to the direction of applied force. That's why it is called lateral. Longitudinal change is change in length. The lateral change means that change happens perpendicular direction to the force. It is called lateral change. That is nothing but change in radius. So the ratio between, what is that? Lateral strain and longitudinal strain. Longitudinal strain is called what? Poisson's ratio or Poisson's ratio. Right? Mathematically it can be expressed as sigma is equal to lateral strain is due to the radius. So you can write it as delta R by longitudinal change is delta L by L. If length is increasing, this will be positive. When length is increasing, radius will decreases. So let me take this as negative. So minus delta R by delta L by L. So you can also express this as minus delta R by R into delta L by L. Delta R L by R into delta L also. Whereas instead of increasing the length, if you are having a body like this, and if this is a cylindrical object, you are applying force like this, and length is decreasing, then radius will increase slightly. Then in such case, I will take delta R by R by minus delta L by L. Anyway, it is minus delta R into L by R into delta L. If one is positive, another will be negative. That's it. Okay. This is called Poisson's ratio, and it is mathematical expression for this. And we have to remember that the value of this, usually the value of this Poisson's ratio varies over theoretical value concept. Theoretical value, theoretical limiting value, limiting value of sigma is theoretically it varies between -1 and 0. -1 and varies between -1 and half. Whereas practically, it's a practical value of sigma is lying between 0 and half. 0 and half. Theoretical limiting value is lying between -1 and half. Practical value is lying between 0 and half. This is briefly about what we call Poisson's ratio and few points about this. Right? Now let us see here few more important terms, especially in examination point of view. We will come across some special relations related to this moduli of elasticity, especially while calculating Young's modulus. While calculating Young's modulus, if you have a wire and its different parameters are given, you can find out what is the formula for Young's modulus. Y is equal to Fl by A into delta L. These parameters are given, you can calculate. If you are given wire, some cases combination of wires will be given in series or parallel. Such kind of cases, how to find the effective Young's modulus, let us try to understand. Write down as some heading: combination of wires or rods. Combination of wires or rods. Combination of wires or rods. So here we come across two kinds of combinations. One is series combination. What is that? What does this series combination mean and how to deal with this? If you have resist support to this wire of length L1 and area A1 is attached, it is another. It is connected to, it is having Young's modulus by 1. It is made of some material, copper or aluminum, whatever it is. It is connected to another material, another wire made of different material whose length is L2, area is A2, and Young's modulus is Y2. And if you apply a force here, normally it may undergo some elongation, delta L. Then what is this elongation is? Delta L. So overall, the combination, this kind of combination of the rods is called series combination. If one end of the rod is connected to another end of the rod, it's called series combination. Now, if I apply a force here on this area, then let it elongate. The entire combination elongate by delta L. So here we can say that it is elongate. The total elongation is delta L means this will elongate by small amount. This also will elongate by small amount. The sum of the elongations is equal to delta L. Here what you can say is same force will act on both rods. So elongation delta L is equal to elongation produced in the first one plus that produced in the second one. Delta L plus delta L equal to delta L. Is it clear everyone? Now, as from the formula of Young's modulus, because Young's modulus y is equal to FL by A into delta L. From this you can write delta L is equal to FL by A by A into Y. For this combined rod, composite rod, for combined rod or composite rod, if the effective Young's modulus, if we take it as y effective, then we can write y effective here. The delta L can be taken as F, same force acting here for same force, FL by A into y effective is equal to, for this it is, for the first one you can take delta L1 is F L1 by A y1 plus F L2 by A y2, provided if A1 is equal to A2 is equal to A. If areas are same, then you can take A1 and A2 only. Otherwise you have to take this as A1 A2 separately. Now on simplifying, F is same and A is same, then you will get L by y effective what? It is nothing but L effective. L effective or L total, right? Total length, L effective by y effective is equal to L1 by y1 plus L2 by y2. Is it clear everyone? From this, L effective is what? Total length. Total length is nothing but L1 plus L2. So you can take this as L1 plus L2, and hence by cross multiplying you can write y effective is equal to, if you bring this entire thing here, then you will get L1 plus L2 by L1 by y1 plus L2 by y2. This is the y effective. Even if L1 equal to L2, then we can take this as 2L by y1 plus L by y2. L gets cancelled, then we will get if y1 is if L1 equal to L2, then we will get, if L1 is equal to L2, then we will get y effective is equal to 2y1 y2 by y1 plus y2. You have to remember this formula as shortcuts by doing the numericals. If the objects are having same length and same area, and if I ask you to find the effective Young's modulus of the combination, directly you can use this formula as a shortcut. Y effective is equal to y2 y1 y2 by y1 plus y2. Is it clear everyone? When the rods are connected in series, when they are connected in parallel, then how to find this? Let us see. Yes, I have taken this. Next, write down parallel combination. Second one, parallel combination. When two rods are said to be connected in parallel. So in this case, if same rigid support, if I have connected a wire, here another wire of this is having area A1, this is having area A2, and this is, both are having same length, let us say L1, L2, both are having same length, and they are connected to common load, so that the force F is equal to mg is acting over here. And following here, so that usually here, when they are in series, same force will act on both rods, but here force will divide between these wires. So because of different natures and of course different parameters here, force will divide. As a result, so you can say this will divide into F1 and F2. As a result, the both will elongate same amount. That is the meaning of it. When common load is attached here, both will elongate the same amount. Even though they are made of different materials, they are elongating by same amount, means different force are acting on different wires. That's why both elongates by same amount. By using this condition, you can find out what is the effective Young's modulus. In the previous case, elongation is same. Elongation is what they call shared. Here, force is sharing. F is equal to F1 plus F2. Again, by using same, what is that? Young's modulus formula is equal to FL by A into delta L. Here F is equal to by A delta L by L. If they are having same length, L1 is equal to L2, equal to L, and if you consider A1 and A2 are different, then they can find out at the end again if they are same, what will you get? So F is equal to, from this, F is equal to by A delta L by what? L by L. So if you take this here, you can take effective force is nothing but effective Young's modulus into A effective into delta L by L is equal to L effective. Parallel combination L effective is same as L only, is equal to, this is Y1 A1 delta L by L1 plus y2 a2 delta L by L2. If L1 equal to L2, L effective equal to L1 equal to L2, all are same, so this will get cancelled. Effective length is also nothing but same as the initial length. So if they cancel, then we get this one. Even so, you can here, you get even delta L is same, you get y effective is equal to y1 a1 plus y2 a2 by a effective is nothing but a1 plus a2. This is y effective in parallel combination. Even if y is also constant, same. If a1 equal to a2 equal to a, then y effective is equal to a is coming out 2a. A gets cancelled, you get y1 plus y2 by 2 you get. Is it clear? So these are few points you have to keep in mind related to what? Calculation of effective length modulus of two wires connected in series or parallel. Based on this, you will get some questions. In the previous years also some questions are asked based on this. Here you have to remember one more point. Elongation produced in a wire due to its own weight. Due to its own weight. I will give you this basic, the main idea and the final formula. I do remember this. Then you can go through all these points and direct questions. Usually in this direct questions only will come. So you can practice some questions as well. So elongation produced due to the own weight of the rod or wire. So elongation produced elongation due to own weight. To understand this, you have to consider here a wire of total length L, and if a force F is acting over here, you have to understand that if we consider a small element at a distance x of length dx, if you apply a force F, then a small elongation dl may produce. This may be dl. So dl is you can see this force is nothing but weight of the rod. It is nothing but weight, W. Okay? On the entire length, if you say weight is W, on unit length, the weight can be expressed as, the force can be expressed as W by L is weight per unit length, is force per unit length. On this length of this wire, if you want to find what force into dx have to take. What is the weight acting on this is much is the force acting on this is out of this because the mass is distributed throughout. So W by L into dx. This is the force acting F. But stress is nothing but a small amount of stress acting on this can be expressed as ds is equal to force by area. It is nothing but W by AL into dx. Following this is stress. But if you want elongation in terms of Young's modulus, as Young's modulus y is equal to FL by A into delta L in general, this elongation if you want. Elongation from this you can write delta L is equal to FL by A into y. Are you following this? Right. So here the total elongation, this is the stress. You can also write y equal to stress by strain. Stress here F by A is this much. So this can also be expressed as W by AL. This entire thing is this W by AL into dx into L by delta L. Here L is nothing but length of this element. You can write it as x dx by x dx by. You can take it as y. We are taking it as delta or L. We are taking for total elongation, right? Delta L into y is equal to here. So therefore delta L is equal to delta L can be expressed as W by L into delta L is equal to y into x dx. This is the elongation produced in a small length of the wire of length dx at a distance of x. So due to the entire wire of length L, if you want, you have to integrate it. It is entire elongation to take it as L, or elongation E you can take small e or L is equal to integral of delta L, where L goes from 0 to L. So if you take this here, then you will get is equal to integral of W by A and y x dx, and L length goes from 0 to L. So you get this as x square by 2, you substitute this L, then you get L square by 2. L gets cancelled, and hence the total elongation produced due to its own weight due to its own weight is given by, what is that? E is equal to, or L is equal to, you can say it as L square by 2, L gets cancelled, so write it as half into WL by AY. AY will be the elongation produced due to its own weight W. Elongation, write down that. Here you can write a sentence also. Elongation produced due to the own weight of a wire or rod is this. Elongation produced due to own weight. Elongation due to own weight. Own weight of a rod is this. So based on this also some questions are asked in the previous years. Yes, girls? Is it clear? Very good. Boys? Very good. Very good. Right. Following or not? Everyone? Yes, boys? Right. So with this, the mechanical properties of solids is completed. Right. Now, as sir is waiting, very close now. You guys go through this once briefly and practice questions. Simple questions. Okay? Okay, then take care. Bye bye.